5107. Consider the reaction of aluminum chloride with silver acetate. How many milliliters of 0.25 molar aluminum chloride would be needed to react completely with 20 milliliters of 0.5 molar silver acetate solution? All right, so we have 0.5 molar silver acetate. We're just going to abbreviate the acetate ion like that, acetate. Okay, and that's 0.5 moles for every 1 liter, right? So we can change that to moles. So we have 0.5 molar of silver acetate. It's 20 milliliters of that, or 0.02 liters of the silver acetate solution. How many milliliters of 0.25 molar aluminum chloride? 0.25 molar aluminum chloride. So we have Ag acetate, AC for acetate, plus AlCl3, all right? 3 chlorides for 1 aluminum, right? Aluminum chloride, right? And then the product is going to be AgCl and Al acetate, okay? And there's going to have to be 3 acetates for the aluminum. So we have to balance this here. We see that we're going to need 3 chloride ions, 3 silver, 3 acetates. All right? So you see the net ionic equation. It's just silver ion plus chloride ion to silver chloride ion, right? If we were to reduce this down and identify the net ionic equation, it would have to be 3 silver ions, 3 chloride ions, and 3 silver chlorides. So that is kind of misleading there for number 107. Anyway, so 0.5 molar silver acetate over 1 liter, that many liters of silver acetate. Now we're in moles of silver acetate, and for every 3 moles of silver acetate, there's 1 mole of aluminum chloride, right? And we want to know how many milliliters of a 0.25 molar solution. Well, there would be, for every, we want to know how many milliliters. So for every, this is how many moles of aluminum chloride, and we have moles of, the molarity of aluminum is 0.250. 0.250 moles for every 1 liter of aluminum chloride. Okay. All right, so if we convert that liter, 1 liter of aluminum chloride to 100, or 1,000, sorry, milliliters of aluminum chloride, this will tell us how many milliliters we need. All right, calculator. .5 times 0.02 divided by 3 divided by 0.25 times 1,000. And it looks like we're going to need 13.3 milliliters of what is this stuff? Aluminum chloride solution. And this is 5107. 13.3 milliliters. All right. All right, review problem 5, 109. Suppose that 4 grams of solid iron oxide, Fe2O3. So we have iron 3 oxide. Suppose that 4 grams of solid Fe2O3 is added to 25 milliliters of 0.5 molar HCl. So this is added to HCl. The products of this reaction are going to be FeCl3. Let's see. This is 3, right? Yeah. FeCl3 here plus H2O. Okay? So that's the chemical reaction that they're talking about. And if we had 4 grams of iron oxide and 25 mils of 0.5 molar HCl, what will the concentration of the iron be when all the HCl has reacted? All right? So we want to see how many moles of HCl. Let's see, what is this balanced equation here? We need to get a 2 here. We need to get 3 here. We need 3 hydrogens, 3 Cl. Oh, no, we don't have 3 there. We need a 6 because we got 6 chlorines. 6 chlorines, 6 hydrogens, looks like 3 waters there, right? So we have 3 oxygens, 6 hydrogens, 2 irons, 6 chlorines, and 6 chlorines. Okay? So there's our chemical reaction. 4 grams of solid iron oxide is added to 25 mils of 0.5 molar HCl. What will the concentration of the iron be when HCl has reacted? So they're asking what the concentration of the iron should be. That doesn't necessarily mean that there's going to be iron left, but it kind of indicates it because of the question. So we can look at how much HCl we're going to have and find out how much iron there will be left, right? So what will the concentration of iron be when all the HCl has reacted? So 25 milliliters, 0.5 molar. 0.5 moles of HCl for every 1 liter of HCl, right? And it says we have 0.025 liters, that's 25 milliliters, right? And so this tells us how many moles of HCl will be consumed, right? Or yeah, how many moles of HCl there are. And for every mole of HCl consumed, actually every 6 moles of HCl, there's 1 Fe2O3 consumed. Okay? So, what will the concentration of Fe3 be when all the iron, the HCl, has reacted? Well, we can start off looking, we can also look simultaneously here. So this will tell us how many moles of Fe2O3 we can consume. But we don't know how many moles of Fe2, we haven't just solved yet how many moles of iron oxide we have, right? So we can, there's a couple ways to do this, but I want to do this where we solve this separately here. So we have our grams of iron oxide, and we're going to convert that to moles of iron oxide, right? So we have 4 grams of iron oxide, 4 grams of Fe2O3. We can try to find out the molar mass of iron oxide. Molar mass of iron 3 oxide. So 159.69. So if we had 159.69 grams, that would be 1 mole of the Fe2O3. So this will tell us how many moles of the Fe2O3 we have. Okay? Okay, so we have a little bit of a limiting reactant. They're actually asking how much iron ion will be left over in solution, right? So this is how many moles of, So instead of saying moles of iron oxide, they're not asking moles of iron oxide, they're asking how many moles of iron ion there's going to be. And for every 6 HCl consumed, we're going to get 2 iron chlorides, which is going to give us 2 Fe plus 3 ions. Okay? And so this one here is assuming the HCl is the limiting reagent, and it tells us how many moles of Fe plus 3 ions we're going to get. This one here will assume that the iron oxide is the limiting reagent, and for every 1 mole of iron oxide we have, we're going to get 2 moles of iron chloride and iron 3 chloride, and that's 2 moles of iron. So for every 1 mole of iron oxide. All right? So this one, assuming the hydrochloric acid is limiting, this one, assuming the iron oxide is limiting. All right? Both of these will solve for the number of iron ions. So the first one here, 0.5 times 0.025 times 2 divided by 6. All right, so I'm getting 0.004166 moles of Fe plus 3. This one down here, 4 divided by 159.69 times 2. 0.050097 moles of Fe plus 3. So this one is going to be the limiting reagent there. So what will the concentration of that be when all the HCl's reacted? This one. What mass of iron oxide will have not reacted? Okay, so this is how many moles of, let's see, how much of this will have not reacted? Well, what was their question? What will the concentration? Oh, they want the concentration be for the iron 3 when all the HCl's reacted. So suppose that 4 grams of solid was added to 25 milliliters. So if this is the moles, concentration, we have to get moles per liter, right? So we have to assume 0.025 liters. They didn't say anything about the volume change due to adding 4 grams of iron sulfide, or iron oxide. So we have to take this value here, which is 0.004166, and divide that by 0.025. And that should be our concentration, which is 0.166 molar, 167 molar. Okay? All right, so that's the concentration of iron oxide in the end. Iron 3 ion in the end. Now, back to this question, how many moles of this are going to be left over? Well, to solve that, we can find out how many moles there were initially of the 2 compounds, 2 reactants, right? This will tell us how many moles of HCl there were. 0.5 times 0.025. There was 0.0125 moles of HCl. And for this one here, there was 4 divided by 159.69, or 0.0250 moles of Fe2O3, iron oxide. Okay, so this is how many moles of HCl we had. This is how many moles of iron oxide we had. HCl was the limiting reagent. So this, we need 6 of these for every one of these. So if there's 6 of these, if this represents how much HCl we had, then we're only going to be able to consume 1/6 that many moles of iron oxide. So if we take this 0.0125 and divide it by 6, then that should be how many moles, which is 0.00208. That should be how many moles of iron oxide we can consume. So if we take the moles of iron oxide that we have, subtract the moles of iron oxide that we could consume, then we have the moles of iron oxide left over, and the question is, what's the mass? So we have to just take that moles, multiply it by our 159.69. So I'm getting 3 left over. Here is getting 0.02295. Then I multiply that by 159.69, which is grams per mole, because this is how many moles we had left over. And I'm getting 3.67 grams of iron oxide left over. Kind of a tricky one there. 5 109. All right, 1167, yeah, we got it. All right, 5111. In a titration, 23.25 milliliters of 0.105 molar sodium hydroxide was needed to react with 21.14 milliliters of HCl. What was the molarity of the acid? All right. So we had 0.105 molar NaOH. And we had 23.25 milliliters, or that many liters of sodium hydroxide. This is moles. I can change that molarity to moles per liter, right? So this will tell us how many moles of sodium hydroxide we had. We have to know the chemical reaction that's occurring here so we can know the stoichiometry. And this is the chemical reaction. You see that it's a 1-to-1 ratio. That's balanced, so it's a 1-to-1 ratio. So this now we're now in moles of sodium hydroxide. When we take the molarity multiplied by the liters of the solution we had, will be in moles. So now we can say for every 1 mole of sodium hydroxide, there was 1 mole of HCl consumed, right? And so now we're in moles of HCl. What was the molarity of the HCl? Well, this is how many moles of HCl. We're in moles of HCl now. If we just divide by, we're looking for big M, which is moles per liter, right, of HCl. So if we just divide this by how many liters of HCl there were, which is 0.02145. All right, this is how many liters of HCl there were. Therefore, we're in moles of HCl divided by liters of HCl, and that should tell us the molarity of the HCl. 0.105 times 0.02325 divided by 0.02145. All right, so I'm getting a molarity of 0.114 molar, and that was number 111. Okay, good. Lactic acid is a monoprotic acid. Monoprotic means monoprotic, protic referring to protons. So 1 hydrogen comes off. Monoprotic acid, where are we at? 113. Eraser it. That forms when milk sours. 18.5 milliliter sample solution of lactic acid required 17.25 milliliters of 0.155 molar sodium hydroxide to reach the end point of the reaction. How many moles of lactic acid were in the sample? How many grams of lactic acid were in the sample? All right, so lactic acid, CH3H5O3. So we need to have a chemical reaction here so that we can know our stoichiometry. They told us it was monoprotic, so that helps us. With sodium hydroxide, which is monohydroxic, if you want to say, 1 hydroxide ion, it's going to be a 1-to-1 ratio, but we can write out the equation anyways. HC3H5O3. Now, this helps us remember it's an acid, right? This proton here is separate from these 5 hydrogens here, all right? So that reminds us that that is an acid. Plus NaOH, the products are going to be sodium, the lactic acid, the lactate ion, right? C3H5O3, C3H5O3 plus water. And it's a 1-to-1 ratio. Okay, so 0.155 molar or 0.155 moles for every 1 liter of sodium hydroxide, right? And it required 17.25 milliliters or 0.01725 liters of our solution. Now we're in moles of sodium hydroxide. For every 1 mole of NaOH, we have 1 mole of, I'll just write La for lactic acid. So I solve this, and that should tell us how many moles of lactic acid. How many moles of lactic acid were in the sample? So that should be the answer for that one. 0.155 times 0.01725 All right, so I'm getting 0.00267 moles of lactic acid. All right, how many grams of lactic acid were in the sample? Well, we have to know the molar mass of lactic acid. We could add all that up. It won't take too long, but I'll bet I can still beat it doing this. Molar mass of lactic acid. Try again. Molar mass of lactic acid. .8. So we had 0.00267 moles of lactic acid, and for every 1 mole of lactic acid, there's 90.08 grams of lactic acid. Okay, so that value that we had before, the moles times 90.08. So that's 0.241 grams of lactic acid. All right, let's double check that. 5 for 13. They're giving us, yes, that's right. 1, 2, 3. It's in scientific notation. That's right. And 0.240. I think it should be 241. Oh, why wouldn't it be 241? Anyway, great. Okay. 115. A certain lead ore contains the compound lead carbonate. All right, so there's a lead ore. Ore just means a big chunk of rock. And inside this chunk of rock, there's some chemical lead carbonate, right? A sample of the ore weighing 1.526 grams, so the whole rock, 1.526 grams. So there's our rock. Has lead carbonate in it. Sample of the rock that had that much mass, 1.526 grams, was treated with nitric acid, which dissolved the lead carbonate. The resulting solution was filtered from the undissolved rock and required 29.22 milliliters of 0.122 molar sodium sulfate to completely precipitate out the lead as lead sulfate. Okay? So it required 0.122 molar, 29.22 milliliters of 0.122 molar sodium sulfate. So we got 0.122 molar. 0.122 moles of Na2SO4 for every liter, and it required from that 0.02922 liters, right? So this tells us how many moles of sodium sulfate. Well, we have to look at how many lead, what the reaction is. Sodium sulfate was interacting with lead ion. What was the lead ion before? It was a Pb+2 ion, right? So we have the lead and sodium sulfate interacting with the lead ion here. So we have to balance this equation first. The product is going to be lead sulfate, solid. That's it, no parentheses there, SO4, solid. And sodium, what? Well, it's going to be sodium, whatever was in the solution, the nitric acid we added, right? So sodium NO3, where are we at? Treated with nitric acid, HNO3. So it's probably going to be sodium nitrate, but that's all right. Okay, so we need 2 sodium ions, and that's it, right? Okay. So we don't even really have to worry about the first part. The first part is where lead carbonate is consumed by the nitric acid, but they don't tell us how much nitric acid they use, and they aren't asking any questions about how much lead ion was produced, or I mean, how much nitric acid was required, right? They just said that they put in nitric acid, and the lead carbonate was converted to, well, I guess we do have to know that when we put lead carbonate, which is a solid, with a strong acid, so you put lead carbonate with a strong acid, it tells us that dissolved the lead carbonate, meaning that it made the lead ionized the lead, made it the lead ion, got rid of the carbonate. Okay, so, and we can write down that reaction. right? Just to kind of remind ourselves, PbCO3 plus HNO3. The products here are going to be H2CO3 and PbNO3, right? And we're going to need 2 nitrates for every lead ion. So this shows here that we're going to need 2 of those, correct? 2 protons, 1 carbonate, 2 nitrates, 2 nitrates. So this is the first reaction that they allude to. They don't ask us anything about it. They just tell us that the lead was dissolved, which is true. The net ionic reaction here is PbCO3 going to, well, H2CO3 breaks down into carbon dioxide and water, right? So we have carbon dioxide and water, and we have H plus ion here, and we have Pb plus 2 ion there. But the nitrate is a spectator ion, so it's not included. Yeah, so that's what the reaction is. So you see that the nitrate, or the sodium ion here is a positive charge. How can it just have a positive charge? Well, it has plenty of nitrates in solution to stabilize that positive charge. Okay, so this is what we got. This is how many moles of sodium sulfate it required. For every 1 mole of sodium sulfate, there's 1 mole of lead sulfate. So I'm going to erase this little part up here, just to give myself a little more space. But that was the first step that they did. But we don't need to understand that specifically for this problem. Now we're in moles of sodium sulfate, and for every 1 mole of Na2SO4, we get 1 mole of lead sulfate, right? All right. So now this is how many moles of lead sulfate, but what other questions they ask? How many moles of lead were in the original sample? Well, for every 1 mole of PbSO4, that's 1 mole of lead. So it's a 1-to-1 ratio, so I can just find out how much lead sulfate there is, and that should be how many moles of lead there are too. 0.122 times 0.02922. And that should tell me how many moles of lead there are. 0.00356 moles of lead atoms, right? Or, yeah, right. Okay, how many moles of lead were in the ore sample? How many grams of lead were in the ore sample? So to go from moles to grams, we just use the periodic table and multiply our moles that we got here times the molar mass, which is 207. Atomic mass of lead. Okay, so I'm getting how many moles of lead? 0.00356. I'm getting 0.738 grams of lead. What is the percentage by mass of the ore? Well, 0.738 divided by 1.526, which was the original sample of the ore, times 100, we're getting 48.4%. 48.4% lead. So we got 0.356, 0.00356, or 356 times 10 to the minus 3, 0.7386, and 48.4%. Very good. That's it. What a hard chapter. Okay, great.